Okay, today we are going to start with the last chapter in this course, which is the frequency response and filters. Okay, so in this chapter we are going to learn how to find the frequency response for a transfer function. In last chapter we talked about the transfer function, and we said transfer function is a relation between the input and output of any systems. It can be electrical system, mechanical system, electronic system, whatever. We have input to that system and we have output, we have component of that system which represent the transfer function for the system. So based on the component of that system, the relation between the output and input will be changed, and the transfer function is used to calculate that relation between the output and input. And we see how, if we have some given information about the input of the system, like input voltage source, input current source, we can calculate the output of that system in the frequency domain. I mean, not in the time domain like we learned before in the circuit analysis. Okay, so today we are going to continue on this part, which is for the for the transfer function. So how to use this transfer function, or how to calculate the frequency response of the system from the transfer function. So these are the expected outcome of this chapter here. So at the end of this chapter, you're supposed to learn how you can draw the body plot, so and how we can use this body plot to identify the different frequency response for the system. Then the relation between the body plot and the filters, because we are going to talk about the filters at the main at the part of this chapter also. So for the filters here, in this case, we are going to study about the low pass and high pass filters, and which consists from RL or RC circuit and so on. Also, we are going to learn how to design some filter based on specific cutoff frequencies. So we are going to connect. Previously when we see the circuit like resistor, capacitor, and inductor, you just analyze the circuit without any without any information about the filters. But now you are going to see how these components can be used to perform or to form either active or passive filters, and how this filter will be used to filterize some specific frequencies which are unuseful or are not used when we want to receive some communication signals. Okay, so usually these filters are used to filterize the signals. Sometimes we use the filter to remove the noise from the signals, like for example in the radio channel, in the communications channels, and so on. When they send the signal with some frequencies, which is with some noise, and this noise, it has its own frequency. So in order to receive the signal without any noise, we are going to use such filter, either low pass filter, high pass filter, all pass filter, band pass filter, whatever is the type of the filter. So these filters are used to remove the undesirable signals or undesirable parts from the communication signals. Okay. So these are the content of these chapters. We start with the frequency response and the definition of frequency response, and how we can find the frequency response for a specific signal, for a specific system. Then we are going to learn how we can draw or sketch the body plot from the given transfer function. From this body plot, usually in the control systems, what they use it also to find or to study the system stability. But we are not going to focus on this part here, because this is, under the control system, this body plot is used to find something we call it like phase margin and gain margin, and these two values are used to investigate what the status of the system, is it stable or unstable, and so on. But here we are going just to learn how to draw this body plot and how we can identify the different frequencies for low pass and high pass filters. Then we are going to talk about the type of filters, filter characteristic also, and how we can analyze the transfer function of the filter.
Doctor,
Yes.
there's someone who wants to enter the class.
What do you think? Should I allow him to enter or no?
I think yes.
Okay.
Thank you.
Okay. So for frequency response here, when we want to define the frequency response, it is as we mentioned when we talk about the in chapter 4, when we talk about the Laplace transform, we said there are some type of signals which used to test or to apply to the system. Then we check the system response either in time domain and in frequency domain. And we mentioned in the table in chapter 4 that we have like pulse function, we have like parabolic function, ramp function. Some of these signals are used to be applied to the input of a system. Then we measure the system output based on the given transfer function. So usually for the frequency response here, the focus is more on one type of the signal, which is the sinusoidal signal. So we assume that the system has an input, which is a sinusoidal signal, and the sine signal will apply to the system, and it will generate a response at the output of the system. Usually this or the linear network or inside the system is represented by its transfer function. As we said before, transfer function can be right as GS or HS or any value here. But in the when we talk about frequency response, our focus will be more on the omega value. Why omega value? Because omega here, as we know, S can be consist from real part. When we represent by using S plane, we said we have real part and we have imaginary part. The real part is the sigma value, and the imaginary part is the J omega. So in the case of frequency response, our focus will be more on the J omega value. We ignore, we do not focus on the real part. We focus more on the imaginary part or on the frequency part here. So as we can see here, in this chapter, we are going to see either GS or GJ omega or HJ omega. Whatever is the value here, it is a function of this variable. Okay. So the as we mentioned before, filter is important here and also significant in the to allow or block some of a specific frequency. And we said like there will be like some of the filter, they call it like low pass filter, high pass filter, band pass filter, all pass filter, and so on. So this type of filter actually more depends on the range of frequency. So our focus will be more on the frequency value. So without the filters here and without the frequency response, it is impossible to receive some of the communication data or communication signals here. Like as I mentioned before, for the radio case here, when you adjust the radio here or the radio channel, you need to adjust some of the frequencies. So for example, this channel, this radio channel send at 89.9, the other radio channel at 90.8, other either kilohertz or megahertz, whatever is the frequency here. So this the channel of the or this frequency is for the data or for the communication signal, while the signal for the noise will be like either lower or higher. For that case, we need to use such filter. So as we said here, frequency response is more focused on the sinusoidal signal, and the operator S here will be replaced by the operator G omega, or it's more on the imaginary part of our frequency. There is actually a direct relation between the time domain and frequency domain, as we mentioned before when we talk in chapter 4. So even we write our equations or our variables here or our functions in terms of omega or in terms of S, but still if we apply the Laplace transform or Laplace inverse transform, So there is a relation between the frequency domain and the time domain. Sometimes we need to apply Laplace, sometimes we need to apply inverse Laplace in order to return the function into the time domain or convert it into the frequency domain. Also, the frequency response here, it has a direct relation with the steady state response, and this is one of the type of the response of the system for a specific input. So as we mentioned before, when we apply like delta signal here, delta of t or ut or t to the input of the system, then we measure its output. The output, we call it like the response for this function or the system response to this function. So we have the transfer function here, which is gs, for example, and we have the input to this system like ut. So we said we have output here of the system. This is the input. We mentioned it like rs. The output is cs, and we said gs equal to cs over rs. So based on the value of the input signal, the value of the output will be changed. Whatever, because output usually equal to cs is equal to rs, which is the input time gs. So if you have rs change, one time it is ut, one time is delta t, one time is sine omega t, whatever is the value of the input here, for sure our response of the output will be changed. But in this case, in the case of frequency response, only we have one type of the signal, which is the sinusoidal input signal. In the case of the sinusoidal here, so that there will be like, or the impact of our system on the input signal will be on both on the magnitude of the input signal and on also the phase of the input signal. So we have two variables. I mean, when we talk about, if I said the function of the voltage here, Vt is equal to 10 sine omega t. Okay, so I have, this is the voltage source, which has a value of 10 sine omega t. That means the output or the value of the voltage here will be changed with the value of the time. So if time equal to 0, there will be a value. If time equal to 1, there will be a value, and so on. Since it's sinusoidal here, like this one. Okay, so the value here of the voltage will be changed with time. Sometimes it is peak value, maximum positive value, maximum negative value. Sometimes it is 0. Sometimes it is in between 0 and the maximum value, and so on. So this value here, it has magnitude, which is 10, and it has also phase. So the phase here based on the shift here, as if you remember when we studied the circuit analysis, there is omega t plus 30, omega t plus 60, and so on. This we call it the phase, or when we have the representation of the phase diagram for the signals. So this we call it the phase angle. Phase angle, for example, this is with 0 phase angle, this is with 30 phase angle, this is with 90 phase angle, and so on. So this we call it the phase shift. So if the signal applied to any system here, when we represent this system by block diagram, this block diagram can be any circuit that you learn, RL, RC, whatever is the component of this system. So we have input source, we have output value. Okay. So that when we have any input here, this input consists from magnitude and consists from the phase. So in the case of the output, if we want to measure the output, we will see how this system component will affect the input of or the input signal in terms of the magnitude and in terms of the phase as well. So when we talk about frequency response in this chapter, we are going to see two main variables. One, we call it the magnitude, and the other we call it the phase. So both of them will be used to represent the frequency response of any transfer function of electrical systems. So the frequency response here can be measured or can be calculated for both, either for a single frequency, when we said, if I said h of omega equal to, for example, 2 omega here, or plus 2, for example, in this case. So this is for a single frequency can be represented, for multiple frequency can be represented. I mean, if omega here change for different frequencies like 10, 100, 1000, whatever is the value. Also, it can be represented for multiple frequencies. So as you can see here, this is our input signal, which is sinusoidal here. This sinusoidal input signal with phase shift, with the value of phase shift is phi here, and it's go through a system. This system, it has this transfer function. So its transfer function either GS or HS or H omega here in this case. So for example, this is H omega equal to M omega. Oh, sorry. H omega equal to M, which is the magnitude with the angle of omega here, or phi of omega. Magnitude for omega, for each value of the frequency, we have a magnitude. For each value of the frequency, we have a phase. Okay, so this is depends on what are the component in our electric circuit. Is it RC circuit? Is it RL circuit? Is it RCL circuit? I mean, resistor only, capacitor only, inductor only, whatever is the value. So it will be used here to represent our electric circuit, like we use or like we calculate the transfer function in chapter 4. We have some circuit, we calculate each transfer function by using, we write the equation, then we represent the transfer function. This is the transfer function. What happened to the signal when it goes through the system? It will be affected here. And this is how it looks at the output of our system. This is the output. As you can see here, the signal here is already different, because here you can see the value of the angle here, the shift is become bigger. Okay, so V out here, or the phase angle for the out, equal to V in, which is the original one, plus phi here. Phi come from, or this angle come from the component of our electric circuit. When we say component, this value of phi here depends on the value of R, the value of L, the value of C. Now look, let me ask you here. If I have in my circuit here, I have a voltage source and I have a resistor only. This is voltage source VT and the resistor only, which is R. What will be the value of the voltage here in this form as a magnitude? If I say this one is like 10 or VRMS here, VRMS value is equal to 10 volt, for example, for this one. Now, if I want to write the phase here, or the value of the voltage in the form of this magnitude and phase, what will be the value of the voltage in this case? If I want to find V as a phasor value, phasor, or as a polar form, means consists from magnitude and angle here. So V equal to what here? What is the value of M? What is the value of the angle? If I have VT equal to 10 volt as RMS value, so what will be here? What will be the angle in this for this circuit? Okay, tell me the angle only. Anyone?
M is 10, sir.
Sorry?
The voltage is 10.
10, okay. The angle?
0.
0. So if you have L here without R, only L, what will be the angle in this case?
90, sir.
90. Okay, thank you. If you have capacitor?
Negative 19.
Okay, thank you. So if you have only one element here, you have three options. If you have only R, the angle is 0. If you have L, the angle is 90. If you have C, the angle is negative 90 of this voltage. But if you have a combination in this case, like R plus L, or R plus C, or R plus L plus C, so in this case, you will have a different angle. It will not be 0. It will not be 90. It will not be negative 90. The value here will depend on what is the value of R, what is the value of L, because in this case, the angle that we are talking about here for the voltage is represent the angle of Z. So if Z equal to 5 plus J5, that means it is consists from resistor plus JXL, which is a inductor. So in this case, for example, the angle will be tangent inverse here, 5 over 5, which is 1. So what is the tan inverse of 1? So this will be the angle of your, of your impedance, and it is also the angle of your voltage of the circuit. Okay, so as we can see here, the input sinusoidal signal has different, the output signal here has a different phase because of the phase of the component inside the system. So if you have RL, if you have RLC, whatever here, it will affect the phase of the output signal. If you have also for the magnitude here, the magnitude maybe it will be the same. The magnitude will be the which is the M out will be the multiplication of the original magnitude which come from the input signal and the magnitude of the system itself, or the gain of the system itself. So you will be multiplied by MIM. If the gain is 1, so it will be the same. If the gain is 10, it will be 10M. If the gain is 10 MI, 100 MI, depends on what is the gain of your system. Okay, so this is what we mean by the frequency response. Frequency response represents the variation of the output signal with respect to the input at specific frequencies. So when the frequency change, we'll get different output signal here based on our component of the transfer function for our electrical system. So as you can see here, this is how we can represent it in equation. M output with the phi output, or the angle or the phase of the output signal, is equal to the M times M. Why M times M? Because if you have two polar number or two complex number in the polar form, like 5 with angle of 20 times 10 with angle of 30. So when you multiply, the polar number will be 5 times 10, it will be 50, and the angle will be addition. So it will be 20 plus 30. If you have 5 with angle of 20 divided by 10 with angle of 30, so you are going to divide 5 over 10 is equal to 0.5, and the angle will be subtraction. So 20 minus 30, it will be negative 10. So this is how we can apply the the operation or mathematical operation on the polar form of complex number. So the combination of the magnitude and phase here, we have magnitude and we have phase frequency response called the frequency response. That means the frequency response consists from two main parts. One related to the magnitude and the other is related to the phase. So later on, when we are going to draw or to sketch the body plot, we are going to represent two graphs. One graph for magnitude, another graph is for the phase variation with respect to the frequency. Zero and volts, we already mentioned for this one in chapter 4, and we see the transfer function, it has zeros values, which make the transfer function equal to 0, and this represents the value of the roots for the numerator, like Z1, Z2, Z3, so it will be like S plus Z1, S plus Z2, and so on. So Z1, Z2, Z3, all this one, we call them the zeros. And the poles are represent the values which make the transfer function equal to infinity. So, or make the denominator of transfer function equal to 0. Okay. So this is how, what we mean by the poles and zero. The poles and zero here of the transfer function are very important to, to form the shape of our frequency response. Depends on the value of zeros and the value of poles and the location of zeros and the location of poles, we are going to have a different shape or different graphs for our body plot. So just to recap on the logarithm here. So for the logarithm relation here, we have two types of logarithm. One is to the base of 10 and one to the base of e. So you have to just go through these two types of logarithm, how to perform operation, multiplication, division, and so on. So how to convert from one form to another form, because for the logarithm here is used in the frequency response in the Similog paper. So we have Similog paper, the one that we are going to use to draw our Pauti plot. So this Similog paper actually depends on these logarithm operation relations. So as you can see here, log P1 B2 equal to log P1 plus log P2, log P1 over P2, log P1 minus log P2, log P to the power of n equal to n log P, log 1 equal to 0, log 10 equal to 1, whatever is the value here. So just we are going to use these properties in our calculation for the frequency response. So this is how the Similog paper or Similog graph paper looks like. Usually it's come with a division, small division. It's not like the normal graph paper. The normal graph paper, it has an equal distance between each two lines. So for example, it is like 1 centimeter squares. So this 1 centimeter is in the horizontal or in the vertical, it is the same. But for the Similog paper here, the representation is depends on the log representation. So as you can see here, from 1 to 10, we have 10 lines. So the first one is 1.1, 1.2, 1.3 until 1.9, then 2. Then from 2 to 3 also we have 10 lines. From 3 to 4 also there is 10 lines. Whatever is between every two frequencies here, or between every two horizontal value, there will be like 10 log or 10 log values, and each one we call it decay. Decay, that means because we are talking about the 10 like in the years for when we say decade, so it is the same here, which will be we call it for that our calculation or our representation for the graph, it will be like per decade. So if the value change from this point to that point, I mean like here, so it will be like 2 per decade, because from 1 to 2 it is 10 points, so it will be like representation per decade. So as you can see here, the horizontal scale is a log scale. So when we say log scale, that means we have a wide range of value here. We will see later on why we need to use this type of paper here. As you can see, this is more clear. I mean, zoom for this representation. In the horizontal, it is scaled by log values, and these log values will represent the log values of the frequencies. Since we are talking about the frequency response, so our frequencies will be represented on the x-axis here, while our response will be represented on the y-axis. So the x-axis here will be represent or will represent the frequencies, and the y-axis will represent the response. And we said we have two types of response. One is related to magnitude, and the other one is related to the phase. So also this is a recap on the decibel scale. As you know, decibel sometimes used or decibel usually used with the gain. When you talk about the gain, like for example, when we talk about the operation amplifier and so on, we talk about the gain values, and these gain values actually represent like a direct relation between output and input. When we say about the gain, it's somehow similar to the case of transfer function, because the gain also relate between the output and the input. So if the input signal is 5, the gain is 10, so the output will be 5 times 10. It will be like amplify this input signal and so on. So as you can see here, if you want to represent, I mean, when we define the value as a without the log value here, it will be like a direct relation between output and input for the gain. But if you want this value to be expressed in the form of decibel, so in the form of decibel, we need to have like 10 log to the base of 10 for the P2 over P1. This is the general formula for if you want to find the value in decibel. And usually this dB here or dBm or dBi, all these units are used in the communication. So in the communication, when we talk about the signal, we use these units because these units are easily to calculate, because sometimes the value are very, very big. So I mean, like in gigahertz, in terahertz, in and the value of the signal more or big numbers. So they go to, or they used to have such dB representation or decibel representation in order to use, like, instead of saying like 3000, they said 3 dB. So I mean, just to simplify the calculation, to simplify the understanding of how the signal will transfer, what is the loss in the path between the transmitter and receiver, and so on. So all these, there are different type of dB. You can find dBi, dBm, or dB alone. Okay, just dB. So the dB here, we are going to use it also here in the frequency representation or the frequency response of the systems. So as you can see here, the dB represent I mean, the gain in decibel that relate between the output and input. And if we have output power and input power, output voltage, input voltage, output current, input current, output signal, input signal, whatever is the value, so it will be represented by the same formula here, which is like 10 log B2 over B1. For this is the original, we use 10, but when we have some relation between like BT and I mean like power and voltage, because usually the power is equal to VI or equal to V square over R or equal to I square R, or this relation gives to the power. So if this is the original formula, which is 10 log output over input, in the case of the power, this become like 20 log output, I mean 20 log V2 over V1, 20 log I2 over I1. Why? Because we are going to substitute for the value of the power by its original components, which is the voltage and the current. As you can see here. So if you have this, if we have such system here with the input signal resistor of R1, output resistor of R2, and we assume that R1 is equal to R2, or the input resistor is equal to the output resistor, we use the formula for the 10 log B2 over B1. So as we can see here, V2, I mean the B2 here equal to V2 square over R2. So this is V2 square over R2, and the B1 is V1 square over R1. So this is based on the formula of the Ohm's law for B equal to VI. So we just represent each V by each IR value, or each I by each VR value. Okay. So as you can see, since R2 and R1 are the same, so just use like this one. So we can come up with this 20 log V2 over V1, 20 log I2 over I1. So this is how to represent the gain in dB for electric circuit. Either you say 10 log B2 over B1, or 20 log B2 over B1, 20 log I2 over I1. All these value will be in dB, while the ratio between V2 over V1, I2 over I1, when I said like 5 volt over 10 volt. So as a ratio here, volt will go with volt, so it will be like 0.5 as a ratio. But as a dB or decibel, it will be like multiplied by 20 log, 5 over 10, so it will give you a value here in dB. But as a ratio, there is no unit for it. So as you can see here, 20 log V2 over V1, 20 log I2 over I1, 10 log P2 over I1. All this, we call it the log magnitude, or LM for the voltage, log magnitude or LM for the current, log magnitude or LM for the power. So later on, this log magnitude will be used to represent the frequency response for the magnitude, which is the log magnitude and the frequency response of the magnitude. And we have another frequency response, which is for the phase. We are going to see how we can find this frequency response for the phase. So what is body plot here? It's actually the body plot is a sketch or graph. Usually they use it to investigate the frequency, or to study or to analyze the frequency response of a system. This system, as we said, can be electrical, can be mechanical, whatever is the system, but this system, it has transfer function. This transfer function relate between input and output of the system. So they use this body plot is one of the frequency response method to study the system stability. So we can say this system is stable, this system is unstable, This system is represent the low pass frequency. This system represent high pass frequencies. This is the cutoff frequency of this system. That is the cutoff frequency of that system, and so on. So it is like graph using a semi-log paper, and this graph, from this graph we can understand a lot of information about the system behavior or system response in the frequency domain. Okay, so usually here the problem for this or the problem with the transfer function here in the when we talk about transfer function, we talk about the frequency, correct? Because we said differential equation in the time domain, transfer function is in the frequency domain. When we talk about frequencies, as we said, frequencies value are very wide range. So when we said 1 hertz, 2 hertz, 50 hertz, 60 hertz, this I mean for 50 hertz, 60 hertz, when we talk about the power or electrical signal for the power. But when we come to the communication system, we talk about kilohertz, megahertz, gigahertz. That means a wide range of frequency. We are not talking about the 50 hertz or 60 hertz like we talk in the power system. So in the communication, for example, there is some megahertz for FM. There is some, also for AM. There is some frequencies range for GSM model for the mobile communication. There is some frequencies for the 3G communication system. There is some frequencies for 4G systems or LTE frequencies for 5G later on. Okay, so this frequency because this 5G now come up or reach to up to gigahertz. So we start to talk about the sub-gigahertz frequencies. So since this value of frequency is very wide, it's not easy to represent it on the x-axis. So if I want to represent 1 million here, or like 10 to the power of 6, so I need to write like 1, 2, 3 until 10 to the power of 6. So it's not easy to have such wide or to represent such wide range of frequency easily on the x-axis. For that, they go for this log or semi-log paper or log representation of frequencies. Okay. So this plot here, we call it the body plot. Body plots either show magnitude, as we said, or show the phase in the degree. So the magnitude here will be log magnitude in decibel, and the frequency, the phase will be in degrees. So we have two graphs for body plot. One for magnitude, one for phase or degrees. So the log scale here is used for body plot because of the range as frequency, as we said, and the representation here in for the x-axis we talk about 10 to the power of 1. For 10 to the power of 2, this will mean 100. 10 to the power of 10, this will be like, we talk about 10 giga and so on. Also, if it goes to the points, the values which is less than 1, so we go to 10 to the power of -1, 10 to the -2, 10 to -3, and so on. So let's go for the range with the integer values, or also for the range for the float values. Okay, usually the body plot is plotted on the semi-log paper that we already see before. Okay, so we said there is two type we need to draw, or we need to sketch. Log magnitude, we call it LM, and this represents the log magnitude with the frequency. So the x-axis here represent the frequencies, the y-axis represent the log magnitude in decibel. So this is in decibel here, or in dB, and this is in the frequency in hertz. So here we have like 10, 10 to the power of 2, 10 to the power of 3, 10 to the power of 15, whatever is the value, it is in hertz, and here is in the decibel. The second plot here, which is the phase also represent on the same axis. For the x-axis, it is frequency. On the y-axis, we call it the phase or angle. So this phase or angle represented by degree. So we have 0 degree, 30 degree, 45 degree, 90 degree, 180 degree, whatever is the value. So it will be in degree. So to represent the phase plot. So body plot consists from two graphs. This is a sample for body plot, and it's generated by MATLAB. So you can use MATLAB to generate the body plot for any transfer function just by very simple command here. There are actually different types to represent the body plot. If you just Google for it, you have this one of the form, which is represent the numerator, the denominator, and also you draw the numerator with denominator by body. So just 3-line commands, it can generate for you the body diagram for your transfer function. So this part consists from magnitude in dB, and here we have the phase in degree. And in the case of or the body plot that we are going to draw by using the manual method, I mean with that software, it will be like approximation for the original body plot. So it will not exactly the same as the one generated by using MATLAB. Okay, so we are trying to approximate because we cannot draw such a slope here or such round on the top. So this line, it is like will be represented by straight lines until this point. Then this line will be represented by a straight line until this point. That line will be a straight line until that point. So I mean, it will be more, or it will be approximation of the original body plot graph that will be generated by using MATLAB, but it will be considered as a correct representation because sometimes it's not easy to generate the graph for such small change values here in the frequency response. As you can see here, manually. So for that, they go for approximation method by using the normal or the manual calculation. And the same is in the case of the phase here. As you can see here, the phase start from 0, a little bit increase, but until some point it will be like considered as 0. Then it will go for 90 or 45 or 60, whatever. Then it will go straight. I mean, all the representation will be without curve, without round. It will be direct representation with line. It will be like linear representation of the frequency response. Usually, as we said, the one that we need to draw here is the transfer function. So whatever is the value that we want to draw here, is it g of j omega, h of j omega? Actually, sometimes because some system they have some feedback, and it consists from two parts, like transfer function here for the forward and for the backward here, like a feedback that they use for the sensor and so on. So at the end, our aim is to draw what is the value of this transfer function. Regardless what is the name or what is the variable. Is it HS? Is it GS? Is it J omega, JS, omega only, whatever is the value? Don't give a lot of attention to such representation. Only, because you do not have enough background about the control system for, the open loop, the closed loop, you just consider such transfer function for the system will be given. I will give you, for example, in the system will be given the transfer function. Is it HS? H J omega or H omega or J omega? G J omega or G omega. Whatever is the value here represent your transfer function for your system. Either this part combination or this part alone or this part alone. Okay. So whatever is the transfer function will be given, you need to draw the body plot for it. Okay. Is this the forward? Is it for the sensor? Is it the combination of the closed loop transfer function? There is a standard form for the transfer function that you need to convert the given transfer function into its form. Okay. So this is, we call it the standard form. I'm not talking about this part. I'm talking about this standard form from here. Whatever the transfer function that you will be given, you need to convert it to such form. Such form mean what? You can see here all plus 1, 1, 1, 1, 1, 1. If you have s plus 3, okay, don't leave it s plus 3. No, it should be like, first you need to make it like s over 3 plus 1. Then represent s by omega. So it will be like omega over 3 plus 1 or j omega over 3 plus 1. Okay. So whatever is the transfer function that will be given, or you will find it for the system, because as we say, the most common representation of transfer function is s, because it's come from the Laplace transform. But if we want to draw the frequency response, we need to represent each S by either omega or J omega. That means our focus will be on the imaginary part of the S operator only. Okay. But here, what we need to do, we need to make it like unity here, plus one, plus one, plus one. So I mean, the value here of the zeros or the value here of the poles will be used to decide later on, is it low pass filter, is it high pass filter, is it derivative, is it integral, whatever is the value. So this is the standard for each for any transfer function. We will stop